Remember, electricity is dangerous. You should be properly trained and follow all safety procedures before working with electrical systems. Most people have seen current transformers, but do you actually understand how they work and the principle behind them? Current transformers come in a variety of sizes and shapes, but they all operate on the same fundamental principle. In this video, we're going to break down how a current transformer, CT, actually works, the principle behind it, and how to choose the right one for your system. We'll also tie in Ohm's law to show how current is measured accurately. And at the end, I'll show you a practical way to use a CT for early ground fault detection. A current transformer, CT, steps down high AC current to a smaller, measurable value. For example, 200 amps in a circuit can be reduced to 5 amps on the secondary. That conversion is called the CT ratio. One thing I've realized over the years, understanding comes from seeing why something behaves the way it does, not from memorizing procedures. That's one reason I like using Brilliant on a regular basis. They're sponsoring this section of the video. Brilliant is an interactive learning platform for math, coding, science, and problem solving, built around learning by doing. You work through problems yourself, test different inputs, and immediately see how changes affect the result. For example, their digital circuits course takes you through how logic signals move through a circuit step by step, so you understand how the system is actually operating. And honestly, that's the same process used when troubleshooting digital circuits, tracing signals stage by stage to figure out where the logic changes. The courses are created by instructors from MIT, Harvard, and Stanford, and they're made for both young learners and adults. You start with the fundamentals, strengthen them step by step, and then build into more advanced concepts without feeling lost. And because the lessons are short and interactive, it's easy to keep learning consistently, even with a busy schedule. To start learning for free for 30 days, go to brilliant.org/electricalad, scan the QR code on the screen, or use the link in the description. You'll also get 20% off an annual premium subscription with full access to all courses. A current transformer works on the same principle as a standard transformer, but instead of stepping down voltage, it steps down current. The primary side is simply the conductor passing through the CT, while the secondary is the winding inside it. When current flows through the primary conductor, it creates a magnetic field, and that magnetic field induces a current in the secondary winding. This is magnetic induction. The relationship between them is based on the turns ratio. As the number of turns on the secondary increases, the current is stepped down proportionally. In most CTs, the primary is just one turn, the wire itself, which allows high current to be safely reduced to a lower, measurable value. Now let's walk through a simple example. Assume the primary current, I1, is 200 amps. The primary has one turn, which is the conductor passing through the CT. If the secondary has 40 turns, then based on the turns ratio, the secondary current, I2, is reduced to 5 amps. So if I place my multimeter on AC amps and measure the secondary side of the CT, I'll read 5 amps, which actually represents 200 amps flowing in the main circuit. But in most cases, we want the meter to display the actual system current. So the reading is scaled using the CT ratio to show the full 200 amps. So how do we do that? One way to do that is by using a current panel meter that can be programmed to scale the CT signal and display the actual current flowing in the system. In many cases, we use an analog meter that matches the output of the current transformer, but it's calibrated to display the actual system current, which in this case is 200 amps. Now, what if we want to bring this current signal into a PLC? Most PLC analog inputs are not designed to read AC current directly from a CT. Instead, they typically expect signals like 4 to 20 milliamps or 0 to 10 volts. So the CT signal has to be converted into a format the PLC can understand. And that's what we'll look at next. One common way to bring a CT signal into a PLC is by using a scalable AC amp panel meter with a 4 to 20 milliamp or 0 to 10 volt output. The meter is programmed based on the CT ratio, so it displays the actual system current, and its analog output is then wired directly into the PLC analog input card. Another way to bring this signal into a PLC is by converting the CT current into a voltage signal. We can do that by installing a 1 ohm burden resistor across the secondary. Using Ohm's law, voltage equals current times resistance. So with 5 amps flowing through a 1 ohm resistor, we get 5 volts. That gives us a signal the PLC can read. But we also need to make sure the resistor is rated for the power it will dissipate. Using the power formula, current squared times resistance, we get 25 watts. So the resistor should always be rated higher than 25 watts to prevent overheating. This voltage is still AC, and most PLC analog inputs require a DC signal. To convert it, we can use a rectifier circuit with a Schottky diode. The diode allows current to flow in only one direction, converting the AC signal into a pulsating DC voltage. However, we also need to account for the diode's forward voltage drop. A Schottky diode typically drops around 0.3 volts, while a standard silicon diode is usually around 0.7 volts. For example, if we measure 5 volts across the burden resistor, the voltage after the diode will be reduced to approximately 4.7 to 4.3 volts, depending on the type of diode being used. Now we can connect this DC voltage signal to a 0 to 10 volt analog input on the PLC. Inside the PLC program, we then scale that voltage value so it represents the actual current flowing in the system. So how do we select the right current transformer? 1. Primary and secondary current. Primary rating. Choose a CT with a primary rating equal to or slightly higher than the maximum current expected in the circuit. Secondary rating. Most standard CTs use either a 5 amp or 1 amp secondary output for panel meters, protection relays, and monitoring systems. Some modern CTs also provide low current or volt outputs designed for electronic meters and PLC interface modules. 2. Physical type and size. Solid core. Highly accurate and tamper-proof, but requires disconnecting the wires to install. Best for new installations. Split core. Hinge design that snaps directly around existing cables without powering down. Excellent for retrofitting. Window size. The inner diameter must be large enough to physically fit around the target conductor safely, but it should be as small as possible to ensure accurate readings and reduce interference. 3. Accuracy class and burden. Accuracy class. The accuracy class determines how precise the CT is across its operating range. Standard accuracy classes are typically used for monitoring and general control systems, while higher accuracy or revenue-grade CTs are used for power billing and energy metering applications. Burden, rated in VA or voltamperes, is the maximum load the CT secondary can safely drive while still maintaining its rated accuracy. This includes the resistance of the wiring, meters, relays, and any connected devices. The CT's VA rating should always be higher than the total burden connected to the secondary circuit. Now, as a bonus, let's take a look at another powerful use for current transformers, ground fault detection. Let's say we have a 3-phase heater system heating a water tank. If one of the heating elements begins leaking current to ground due to insulation failure, it can create a dangerous condition and potentially become a shock hazard if it's not detected early. One way to detect this is by using a current transformer to monitor leakage current on the ground conductor. The CT is installed around the ground wire, and its output is connected to a panel meter with a programmable set point and relay output. If the leakage current rises above the safe limit, the relay can trigger an alarm or shut down the system. The way this is done is by using a normally closed contact from the relay in the heater's control circuit. If you found this video helpful,